Welcome to a video on converting from Cartesian equations of planes to vector equations of planes. First, let's remind ourselves what the Cartesian equation and vector equation of planes look like. So, Cartesian equations are made entirely of scalars. It's the set of all points, x, y, z, that satisfy the equation ax plus by plus cz plus d equals 0, where a, b, c, and d are usually just integers. The vector form of a plane looks a little more complicated. It's basically the set of points x, y, z that can be expressed as one starting point plus a combination of two direction vectors. So here, this is direction vector 1 and this is direction vector 2. Remember, we need two vectors to span a plane, so that's why there are two direction vectors in the vector equation of a plane. In this video, we're going to look at how it can go from Cartesian to vector equations. So there are two methods we can use to convert. The first one involves finding points, and the second one uses parametric equations to convert. First, we'll look at finding points. This method works by finding any 3 points that lie on our plane, then finding the two direction vectors for us to span the plane. This yellow point corresponds to this yellow position vector in our equation. It's where we're going to start spanning our plane from. Now these two direction vectors correspond to this red and blue direction vector in our equation. These allow us to get from our starting point to the other 2 points. Note, it doesn't have to start from the yellow, but it makes it a lot easier to see how we can span the plane if they both start at our yellow. A problem arises if we happen to choose points that are collinear. When this happens, we're no longer able to span a plane, so we have to watch out for what points we choose. Now, let's do an example. Rewrite the plane 3x minus y plus z plus 8 equals 0 as a vector equation. Remember, our first goal is to find 3 points that lie on our plane. How do we find these points? Well, we can find points by plugging in random values into any 2 of our 3 variables, x, y, and z. If we know all but one variable, we can solve for it and guarantee that our point is on the plane. So, for example, if we knew x and y, that means z is the only variable that we didn't plug in. So we can solve for it because x and y will become numbers. Remember, we're plugging in values for x and y. So z is still going to be a variable, but we can isolate it and find its value. Let's first plug in x equals 1 and y equals 0. So we'll take our Cartesian equation of our plane and substitute in x equals 1 and y equals 0. Now we just need to isolate and solve for z. Solving for z gives a value of -11. Now we're going to write down our point. Our x and y were 1 and 0 respectively, so we're going to place these into the x and y components of a coordinate. The corresponding z value is -11, so we're going to put that into the z component of our point. And just like that, we've already found the first point that lies on our plane. If you only had the variables x and z in your equation, you would still plug in and record y values inside the point. They just won't affect your equation. Now we can move on to the next point. This time, we'll plug in x equals 0 and y equals 1. Isolating for z gives us a value of -7. So, once again, when recording our point, the x and y components are what we plugged in, 0, 1, and our z component is this -7 that we just found. Now for the third point. For this one, we're going to plug in x equals 0 and y equals 0. Substituting these in and solving for z gives a value of z is equal to -8. The x and y components of our coordinate then are 0 and 0, and of course the z component is -8. Now we've got 3 points that lie on our plane. Looking now at the vector equation of a plane, we need to now decide which point we'd like to start at. In our equation, this is the yellow position vector that has no parameter like s or t at the front. It doesn't matter which one we choose, so let's pick the point 1, 0, -11. We're going to take this point and plug it right into that position vector in our equation. Now, we just have to find our direction vectors. Let's start by finding this red direction vector right here. So, in order to find this red direction vector, we're going to have to use the point 0, 0, -8, which is any of the points that are not this yellow one, and this yellow starting point. So our vector is going from this yellow starting point to this black point right here. If we wanted to find this red vector, we're going to have to do some manipulation. So, we can rewrite the point A as some position vector going from the origin right to A. Same thing for B. The point B is just a position vector going from the origin to B. They have the exact same components, one is just a vector. So, notice we can write AB over here. We can change this to AO plus OB. What does this look like? Well, this is saying that AB is the same thing as going from A to O, and then O to B, O to B. We always start from A and then end up B. Going from A to O and then O to B is the same thing as just going from A to B in the first place. So, going from A to O, we can rewrite that as going from O to A, but negative. The negative of a vector flips the direction. So A to O is just negative OA. So going from O to A is the opposite of going to A to O, and vice versa. So, once again, AB is the same thing as negative OA plus OB. Now, we can just rearrange and get that OB minus OA is just going to be AB. And remember, OB and OA were just the points. So you can think of it as just subtracting B minus A. That's all. So going back, if we want this red direction vector, we can just subtract 0, 0, -8, and our starting point, 1, 0, -11. Doing the subtraction gives us a direction vector of -1, 0, 3. Now we can sub this into our red direction vector in our equation. As you might expect, getting our blue final direction vector is the same thing. We just take the other point, 0, 1, -7, and subtract our starting point, 1, 0, -11. Doing this gives us -1, 1, 4 as our direction vector, which we can then plug right into our equation for the last direction vector. Now we aren't quite done yet. We still have to check if our direction vectors are collinear. If they are collinear, then we aren't spanning a plane. We'd just be spanning a line. So we have to make sure our two direction vectors aren't collinear. So to check if our two direction vectors are collinear, we have to see if they are scalar multiples of each other. We can do this by looking to see if each of the components can get multiplied by the same number to get the other. In other words, these two vectors are collinear if I can multiply each of the components of this vector by the same number to get this vector exactly. If I can't do that, they are not collinear. But if I can multiply all these components by a single number to get exactly this, then they are collinear. First, let's compare x components. To get from the red -1 to the blue -1, you just have to multiply it by 1. We'll write that number 1 down and see if we can multiply the rest of the components in the red vector by 1 to get the blue one. Checking the y components, you can easily see where it breaks down. 0 times 1 isn't going to get us to 1. So this confirms that our two vectors are not collinear. We can't multiply the red vector by a single number to get to the blue one. If your vectors do happen to be collinear, you're going to have to go back and replace one of your current points with a new one, and then check if your new direction vectors are still collinear or not. Now that we've confirmed that our direction vectors are not collinear, we're now done. The vector equation of our plane is all points x, y, z that are equal to 1, 0, -11 plus s times -1, 0, 3 plus t times -1, 1, 4. Now let's have a look at using parametric equations to convert. The way this method works is by turning two of your variables, usually y and z, into parameters we can sort of slide and cause your other variable to change. Let's convert the same plane with this method. So our first step is to pick a variable to isolate. Here we'll pick x. Isolating x gives the equation x equals 1/3 y minus 1/3 z minus 8/3. Now, we're going to turn our other two variables, y and z, into parameters. The way we do this is by letting y equal some parameter s and z equal some parameter t. Now we sub in these parameters into our equation for y and z. Believe it or not, we now have three parametric equations. Our first one, x equals 1/3 s minus 1/3 t minus 8/3, and the two parametric equations we just made from y and z. Y is equal to s, and z is equal to t. If you only had two variables, x and z, in your original equation, you should still have three parametric equations. It's just your x equation, or whatever variable you isolated for, will only have one parameter. Still create an equation for the variable that's missing to be equal to a parameter. We are going to need it later on. Now we're going to look at our vector equation of a plane. See how on the left we have three nice equations of x, y, and z? Well, we're going to create the same thing from our vector equation. So first we're going to need to create an equation that uses x. To do this, we're going to look at all the x components in our vector equation, because x is only determined by these first components in our vector equation. So we're going to take all of these and write it out as an equation. Keep in mind, these direction vectors, we're going to bring along the t and the s, because these are getting multiplied by these delta x2's, which are the x components of our direction vectors. So we have to bring along these parameters. If we take them along, we get x equals this equation. Great. Now, we're going to do the exact same thing for the y values. All the y components determine the y component of our point on the plane. So, to create an equation with y, we're going to pick out all the y components along with the parameters, because these parameters multiply everything in the direction vector, and write it as a separate equation. So taking all the y components gives us this equation for y. Once again, we're going to do the exact same thing for z. We're going to look at all the z components of our vector equation and write them out as a separate equation, including the parameters because they multiply by everything. All the z components are these. So now we have three more parametric equations. Keep in mind too that when we pulled out these components, the addition sign, also gets dragged along with it, because these are all adding together. So that means these components, these terms, must also be adding. Now we're going to do some matching. We're going to attempt to match these two equations together. We're going to see what is tied together with what. So, here we can see in this equation, we've colored all the terms without a parameter yellow, all the terms with the S parameter red, and all the terms with the T parameter blue. So, if we do the same thing here and color the terms without a parameter yellow, with an S parameter red, and a T parameter blue, the colors look like this. Notice red for S, blue for T, and yellow for without a parameter. So, we can easily see what is what. This x0 is negative 8 over 3. This delta x1 is this 1/3. And this delta x2 is the negative 1/3. So, we can replace these in our equation. Now we do the same matching process for y and z. But before we do that, we'll show that technically it isn't just a single parameter. Both equations still have a constant term and the other parameter inside them. They're just technically multiplied by 0. Matching the terms in y gives us the parametric equation for y on the right. This same exact process repeats for z. Now that we've nicely arranged our three equations, we'll have another look at our vector equation for a plane. Do you think you can see how everything will fit in? Notice here, this first starting point is in yellow, and it has all constant terms without any parameter on it. And in our parametric equations, we have our yellow terms that have no parameter in front of it. So, as you might expect, these yellow terms are each going to go into this yellow vector right here. The x component is the one from the x equation, the y component is the one from the y equation, and the z component is the one from the z equation. And the same exact thing applies for this red direction vector and this blue direction vector. Each of the corresponding components come from the appropriate equation. Starting with all our x terms, we can take them and plug them each into the appropriate vector depending on the parameter each term has. Same thing for y. We take all the terms in the parametric equation for y and then sub them in to the appropriate vector depending on the parameter each term has. And exact same thing for z. Now I can stop here if we wanted to, but since I hate looking at fractions, we're going to go ahead and get rid of some. So since the only purpose of these direction vectors is providing the direction and orientation of our plane, we can scale them up or down however we want. Remember, the direction vectors, the only purpose they serve is to tell us what direction to go. So it doesn't matter how long or how small they are, as long as they point in the same direction, which, scaling them up and down, will keep them in the same general direction, we can multiply them by a scalar value. So to get rid of those 3's in the denominator, I'm just going to scale both of the direction vectors by 3, so that they cancel and we're just left with whole numbers. Note that we can't do this for a yellow position vector, because that tells us an exact point on our plane. If we scale it up or down, we might end up off the plane. The position vector isn't telling us a direction, it's giving us an exact location, so we can't change it. And just like that, we're done. Notice that we didn't get the same exact answer as our previous method. That's because there's infinitely many ways to write the equation of a plane. These are both correct, they just look different. So before we end the video, let's have a quick look at some of the pros and cons of each method. For the finding points method, a major disadvantage you may have noticed is it's a lot lengthier than the method with parametric equations. Another disadvantage is that we have to check if the direction vectors we got were collinear, so that method isn't guaranteed to work out the first try every time. But a major upside of using that method is that you can tell exactly what you're doing. With that method, you could literally stop anywhere in your work and tell yourself, I am trying to find this on the plane, and it's going to help me do this. As for the other method, you typically get a lot of fractions when you work with parametric equations. Not always, but it's very common to have fractions. The other downside of using parametric equations is it's not very intuitive. While isolating for x in that case, we weren't able to tell what's going on. There wasn't an easy graphical intuition. The answer just seemed to pop out of nowhere. One of the best things about using parametric equations, though, is that they work the first time, all the time. You don't have to worry about checking if your direction vectors are collinear, because that'll be guaranteed for you. You can rest easy knowing that you'll just get the answer right away. And that concludes our video on two methods you can use to convert from Cartesian equation of a plane to vector equation.